Okay, we are off to chapter 12, as I think we wrapped up chapter 4 last time. Like I said before, we're going to go 12. We'll come back to 5 and, some other things, I suppose. All right, so in chapter 12 here, we're going to talk about chemical bonding. We're talk about both types of chemical bonding and all chemical bonding. We will talk about how to draw Lewis structures. We'll talk about molecular geometry, polarity, and all the fun bonding stuff. So let us get into it here. First off, we do use what are sometimes referred to as Lewis dot symbols. They're also sometimes just more generically called just electron dot symbols. To basically represent bonding and both types of bonding, ionic bonding and covalent bonding that we're going to talk about. So when atoms interact with one another to make a chemical bond, as we've talked about, I think a couple of places so far, it really is those electrons that are on the outside that come in contact with each other that's really participates in bonding. And it's actually specific electrons which are the ones that participate in bonding, and those are what are known as the valence electrons. And the valence electrons are the outermost highest energy electrons. And they're really the ones that are involved in bonding. So for example, if we took something like sodium has 11 electrons, also has 11 protons. But in terms of those electrons, if we write something that's known as the electron configuration, by the way, which is something that looks like this: 1s2, 2s2, 2p6, 3s1, and we'll talk about this in chapter 11. But you might see some electron configuration written here in chapter 12 because they probably assume that you do chapter 11 before 12, like how the book's written. But since we kind of bounced around a little bit in this class, that is electron configuration. Let's talk a little bit about some of the things that we see here in an electron configuration. The first numbers here, this 1, 2, 2, and 2, these are what are basically known as the principal quantum number, and that is sometimes abbreviated with an N. That is really a fancy word for energy levels. And the lower the number, the closer the energy level is to the nucleus, and the closer those electrons are to the nucleus. So for example, N equals 1 is the lowest state of energy and closest to the nucleus. N could be N equals 2, 3, 4, 5, 6, 7, and all those are higher states of energy, which means the electrons are further away from the nucleus. So in this particular case, we basically can see where the electrons are located. They're located in what are referred to as orbitals, which we're not going to get into too much detail here, but that's what the S, the P is represented. They're referred to as orbitals, and that's sort of where electrons are in the actual atom. The top number here is how many electrons there are in those orbitals. And if we count up all these top numbers here, that is where we get 11. And that is the total number of electrons there are in sodium. Now, valence electrons are the outermost highest energy level ones. And for the example here of sodium, which one here is the highest energy level it gets to? It is the third energy level, this guy right here, right? And on the third energy level, there is just one electron present, and that is what is known as valence electrons. The lower energy electrons that are on the lower energy level closer to the nucleus are sometimes referred to as core electrons. It is only those valence electrons which are the outermost, and as we'll talk about, not really held as tightly as those core electrons because they're further away from the positive charge that can participate in bonding. Core electrons typically do not participate in bonding because they're like right on the positive charge-ish, and they feel a really strong attraction to that nucleus, and they're held really, really tightly. As you move away from the nucleus and that positive charge, those electrons are not being held as tightly, and makes it a lot easier for them to either be removed or be used for sharing and stuff like that. So when we draw Lewis dot symbols or electron dot symbols, We only really show valence electrons, as those are the only electrons involved in bonding. Keep in mind that these elements do have other electrons that are there, which are those core electrons, which are not involved in bonding. Any questions on that? Now, clearly, you could write the electron configuration to try to figure out how many valence electrons everybody has. Nobody wants to do that. So a much quicker and easier way is to look at the periodic table. And the group number will equal the number of valence electrons. So if you look up there on the periodic table, you'll see sodium is group number 1, and it has 1 valence electron. If you go right next door to magnesium, it is group number 2, and it has 2 valence electrons, and 3, 4, 5, 6, 7, 8 is like we normally would. One exception is in group number 8, and that is helium. So helium, right, is in there in group 8. But it has only 2 electrons total, which means it only has 2 valence electrons, even though it's part of group 8. It's also why, as we will talk about hydrogen, for example, only should have 2 electrons, because the whole goal of bonding, as we will talk about, is pretty much for everybody to achieve the same electron configuration as the noble gases. Noble gases, as we talked about, are chemically inert, they're super stable, and that is what everybody's trying to achieve, to become like the noble gases in terms of their electrons through bonding, both types of bonding, ionic bonding that we'll talk about, and covalent bonding. But that is really the overwhelmingly goal of bonding, is for everybody to achieve just like the noble gases in terms of their electrons. And it's important to also remember, as we will talk about, they do not turn in to those elements. They are still the same elements they started with, but they have the same electron configuration as those noble gases, which makes them really stable. They cannot turn into those elements, because the only way an element can change is what needs to change. What changes, what thing makes something a different element? The number of protons, electrons, neutrons, which one? It is the protons, the atomic number that we talked about, right? That is the one thing that everybody has its own atomic number, right? So when we talk about bonding, it only involves electrons. It doesn't involve anything to do with the nucleus, and we only change electrons. So sometimes people have a misunderstanding of the idea of bonding, that, oh, we're changing these things into noble gases, but they're not. They're still the same elements. But what makes them more stable is they have the same electron configuration as the noble gases. So that's something important to keep in mind. Now, I will say that in most cases for this class, and probably most chemistry classes you come across, you usually will not do any type of drawings of Lewis structures or bonding that involve transition metals, which are those guys in the middle. But if you did need valence electrons for your transition metals, it goes by group number as well, but it goes more by the B numbering. If you remember, there's like an A numbering that we use, and like a B numbering that just runs from like 1 through 18 all the way across. And you would follow that numbering for those guys in the transition metal as to how many valence electrons they would have. So for example, there, if you look at iron, iron is group 1B. I'm sorry, 6B, which means it will have 6 valence electrons. And again, for those transition metals, you could revert to kind of the B numbering, and you can figure out how many valence electrons those guys have. But in most cases, it's just the representative elements, the normal 1, 2, skip the middle, 3, 4, 5, 6, 7, 8. And that is definitely the fastest way to figure out how many valence electrons everybody has. Any questions on that? So for example, here, if I had nitrogen, how many valence electrons should nitrogen have? Five. Five seems like a good answer. I think so. Because nitrogen is group number 5, I think, right? So it's group 5 on the periodic table. It has 5 valence electrons. If you looked at the electron configuration for nitrogen, 1s2, 2s2, 2p3. That's the first energy level, has 2 electrons. Second energy level, 2 electrons, and 3 electrons. That is the 5 valence electrons that it has in that case. Those 5 electrons on the second energy level for something like nitrogen. All right, so let's take a look at some of this stuff here. Lewis dot symbol, like I mentioned, is basically just the symbol. So whatever the symbol is, and basically 1 dot to represent each of the valence electrons. There's really no big rule, I think, other than you should not put more than 2 per side. It's usually the general rule there. That means if I max up all the sides here to my symbol, how many electrons is that? That's 8. I think I have on the paper there, right? So that's 2, 4, 6, 8, 2 per side. And 8 valence electrons would be the same number of valence electrons as group number 8 on the periodic table. Once again, our noble gases. So 8 is a really important number in terms of bonding, is what's referred to as the octet rule that we'll talk about. And again, that again is the goal of bonding, to get to that sort of situation. Here are what some Lewis structures, our Lewis dot symbols look like, or electron dot symbols look like for each of the elements. You see everybody in group 1 has 1. Everybody in group 2 has 2. Once again, 3, 4, 5, 6, 7, and 8, with our helium there being our exception. And as I mentioned before, the goal is for everybody to reach noble gas configuration. That is why hydrogen, once again, only needs to get to helium and should only have 2 electrons. That is something people screw up on a lot. They just like load up hydrogen with hundreds of electrons and dots and lines and stuff like that. Hydrogen should only have 2. Everybody else pretty much should have 8. So that's a really important thing. Again, hydrogen, if you look at the periodic table there, the noble gas that comes right after is helium. So it just needs to get to helium. Everybody else needs to get to somebody with 8, basically, in that column. So let's talk a little bit about the types of bonding and what these Lewis dot symbols will help us understand. And there's really 2 types of bonding that we're going to talk about in the chapter, or in general. And that is ionic bonding. And when we have an ionic bond, it is always between a metal and a non-metal. And what happens when you have a metal and a non-metal that comes together, because of a lot of periodic trends, things like ionization energy, which is the energy required to remove an electron. So for example, ionization energy, which is this guy, is the energy needed to remove an electron from a gas phase atom. Also, electron affinity is the energy change that happens. They run out of room, I'll go this way. When an atom gains an electron. Things like atomic size and things like effective nuclear charge. So let me just back up a page here, I think. I'll do it here. So when we look at some of these trends, which really is in chapter 11, by the way, but it is kind of what your lab's on today. So we'll take a moment here and side trip onto some of these periodic trends. We have several that are really important to understand what happens in terms of bonding. As I mentioned before, there our ionization energy is that energy to remove an electron. And on the periodic table, it increases as you go this way, up and to the right, and decreases as you go down and to the left. There's electron affinity, which is the energy change as a result of gaining an electron. And if you think about affinity, right, it means that you like something, right? You have a like for something. So if you have a high electron affinity, you have a like for gaining electrons. You have a low electron affinity, you don't like to gain electrons so much. On the periodic table, it increases as you go this way, decreases as you go that way in general, not a perfect trend. There's electronegativity, which is we'll talk about here, the ability of an atom to attract electrons. Increases as you go up and to the right, with fluorine being the most electronegative. Decreases as you go down. Atomic size. Bless you. Decreases actually as you go up and to the right, and increases as you go down. That is the size of the actual atom, right? By the way, when somebody loses an electron, that is the formation of a cation, right? And when you lose an electron, do you become larger or smaller, the cation? Cation will then become smaller than the neutral, right? A lost electron, so it kind of shrinks, right? When you gain electrons, right, it actually increases, right? Because it gains some electrons to its field. Another couple of things that sort of tie into some of this stuff that we're going to talk about is what is referred to as effective nuclear charge. And that is what is sometimes referred to as Z effective. And that increases as you go up and to the right and decreases down. So what is that? Let's take a look at lithium, for example, right? If we look at lithium, it has 3 electrons, right? It has 1s2, 2s1, and this is its valence electron. It's 1 valence electron, and that's its 2 core electrons. So on the first energy level, closest to the nucleus, you got a couple of electrons that are hanging out. On the second energy level, you got like 1 electron, which is its valence electron, right? And these guys are its core electrons over here. So what this means is when we look at the relationship of where those core electrons are to the nucleus versus the valence electron, those core electrons are pretty much right near the nucleus. And that means that it feels, those core electrons feel a full brunt of that +3 attraction. The strength of a positive and negative attraction is dependent on the size of the charge. So something like a +3 is going to be a much stronger attraction than like a +1 and a -1. So those electrons, which are the core electrons, basically feel a full +3 charge, and they're going to be held really, really tight. Now, when we get to our valence electron, which is this guy, this valence electron actually is going to experience what is referred to as shielding. So that valence electron is going to basically feel what is known as shielding. So what is shielding? So an example would be, for example, before they assign seats at movie theaters, you just go in and sit down, right? And you get there early, you pick up a nice seat right in the middle of the theater, right? And right before the movie starts, somebody comes and sits right in front of you with a giant cowboy hat on. You can't see half the screen, right? It's shielding basically half the screen up from you. And that is what's happening to this valence electron on the outside. Instead of feeling the full brunt of that +3 charge here, it's got these electrons in the way that are kind of shielding it from that full charge. So instead of it feeling that +3 attraction like those core electrons are, it's actually feeling something like this. You could actually calculate it. The Z effective would be the positive charge, which is 3 for the protons, minus the number of electrons there in the lower energy level, which are 2. So effectively, what that valence electron is actually feeling in terms of a positive attraction to the nucleus is a +1 charge, which means it's not going to be held as tightly as those core electrons are, which is why our valence electrons can be used for bonding. They're easily removed than those core electrons. They're not held as tightly because of that. Any questions on that there? Now, speaking of losing electrons and ionization energy, just so you know, electrons actually do come off one at a time. They don't drop off all at once. So for example, if we looked at something like, we'll do magnesium, for example. Magnesium has 12 electrons. And if you wrote the electron configuration, it'll look something like this. 1s2, 2s2, 2p6, 3s2. These are the 2 valence electrons for magnesium. It's the highest energy level there at energy level 3. It's got 2 electrons. So what will happen in the case of something like magnesium is the magnesium will first lose 1 electron. And we show that by the electron being on the product side there of the arrow, being given off. This is what would happen is the first ionization energy. So there's a certain amount of energy just to remove that first electron. What will then happen is that guy that has a +1 charge will drop off another electron. And that is what is referred to as the second ionization energy. And then maybe that guy with a +2 charge will drop off 1 more electron and make a +3 charge. And that would be the third ionization energy. So ionization energy, there's a first, second, third, fourth, however many electrons you want to try to pull off. They do come off one at a time. So my question is it easier to remove the first electron or the second one? Which one's easier to remove? What do you think? 50-50 shot. First one or second one? Which one's easier? First one's much easier to remove. You got something that's neutral. When you remove that first electron, it all shrinks, right? So now even those outer electrons have now moved closer to the nucleus, and they're going to be held tighter. But it takes a lot more energy to remove the second electron. To remove the second one, everybody shrinks a little bit more. It's going to be a lot harder to remove the third one. So in terms of energy, the first ionization energy is lower than the second is lower than the third. The ionization energy for every electron that you take off, the first, second, third, fourth, whatever, it continuously increases and gets harder and harder to remove electrons because everybody gets closer and closer to the nucleus, right? And now you have a much larger positive charge than you have a negative charge, going to bring everybody in and held a lot tighter. This also explains why when you look at the periodic table, and I think we talked about charges on the periodic table, right? Everybody in group 1 will make a +1 charge, right? When they do make a charge, everybody in group 2 will make a +2 charge. Group 3 will be a +3 charge. Group 5 will be a -3, which are nonmetals. Group 6 will be -2, where oxygen is, and fluorine and all those guys will be -1. So magnesium, which is group 2, will always form what type of charge then? Only a +2 charge, right? Because it's group number 2. And that is because of this reason right here. I get rid of my 2 electrons here for magnesium, which are those 2 right there. Those are my 2 valence electrons. The third one that I am trying to rip off are now a core electron, right? Which is super close to the nucleus now because we got rid of a couple of extra ones. Good luck with that. The energy difference, by the way, as you go from like the first to the second, maybe it goes up by a factor of 4. As you go from like the second to the third, maybe like a factor of 12. Like you got to like super energize it. Not going to happen in most cases. And that's why we don't usually see this happen, because you're into those core electrons and they will not, energy-wise, it won't really happen because of that. It's not very efficient for it to happen. So that's why certain things like in group 1, group 2, group 3 will only form a certain type of charge because energy-wise it's not efficient for them to lose the next electron. It's really a core electron and it's not going to really go anywhere. Any questions on that there? So since we did this, to summarize, here are trends and what it means is, if we look at the periodic table just sort of as a whole here, we have in terms of size, gets smaller as you go this way, gets larger as you go this way. We have ionization energy, which increases as you go this way, decreases as you go this way. We have electron affinity, with increases this way up to the right, down to the left decreases. We have electronegativity, which increases up and to the right, decreases down and to the left. And we have like effective nuclear charge that increases as you go to the right and decreases as you go down. What do all these things basically tell us? When we look at the periodic table and we have like our staircase coming down, right? Up and to the right, that is our nonmetals. And our nonmetals have these properties that make them very small, which means the electrons, even the outer ones, are closer to the nucleus. They're going to be held really tightly and have high ionization energy, have high electron affinity and electronegativity. Those are all trends that say nonmetals like to hang on to their electrons and they like to gain electrons. They don't like to get rid of electrons. And that's why when we think about nonmetals, they have all those trends that make them want to gain electrons. Now, if you go bottom left of the periodic table, you have all the opposite trends. You have size that's really large, which means our outer electrons are further away from the nucleus, not held as tightly. Lower ionization energy, doesn't take a lot for them to lose electrons. They have really low electron affinity and electronegativity, which means they're not really interested in gaining electrons. So they all have trends, our metals, of take my electrons, please, basically. They're willing to get rid of their electrons really easily. And that's why we see metals typically will lose electrons and become our positive cations, or in this case, a lot of times, and why these guys will become anions, especially in the case of ionic compounds. Any questions on that side trip to periodic trends in chapter 11? Any questions on any of those there? Okay. All right. So let's go back to what this relates to, where I took my detour, which was right here, I think. All right. So we were talking about different types of bonds, and an ionic bond is always between a metal and non-metal. So as we just talked about, that means a metal always has the trends that they want to transfer their electrons, or some electrons, to our non-metals. And that will result in our metal becoming a cation, which is positively charged, and our non-metal becoming an anion, which is negatively charged, right? And what holds together an ionic compound together is that attraction between the positive and the negative, sometimes referred to as electrostatic attraction. Important to remember, there is no sharing of electrons in an ionic bond. There is a transfer of electrons that basically occur. And that is very different than the other type of bonding that we're going to talk about, which is covalent bonding. Covalent bonding is between two nonmetals. So why is that important? If we look on the periodic table where the nonmetal located in the exact same periodic table, and that means that they all share similar trends that we just talked about. They all have the trend of, I don't want to give away my electron. I want your electron. They both have basically that sort of trend. And what happens when you get two nonmetals together, the best that they will agree upon is, I ain't giving my electron away. You're not giving your electron away. Why don't we just share? And they end up sharing electrons. And that's what happens because they both have very similar periodic trends. We end up with sharing of electrons. And as we'll talk about in this chapter, may be equal or unequal sharing, but there's some aspect of sharing. And that's very different than what happens when you take somebody that's a metal on the left-hand side of the periodic table with somebody that's a non-metal on the right-hand side of the periodic table. With an ionic bond, you got the metal that has all the properties of take my electrons, and you have the non-metal that goes, cool, I'll take your electrons. And that's why we get those electrons that completely transfer. I'm sure that's the exact conversation that happens. So, any questions on that there? Yeah. So as we talked about, pretty much our group 1, group 2 will most likely form cations. Our halogens, our nonmetals up there are going to be our anions in those cases. So let's take a look at an example of this. This is lithium and fluoride, and this is basically two elements, lithium and fluorine. And in this case, the first thing that you want to sort of identify is what you're dealing with. So lithium is a metal, fluorine is a nonmetal. So to be honest with you, right off of the bat, if you could identify those two things as a metal and a nonmetal, I should know what type of bonding should be happening here. This should be an ionic bond. And that's pretty much the deal. As you see a metal and a nonmetal together, it's going to be an ionic bond no matter what the situation is. Don't think more than 2 seconds about it. Just call it an ionic bond and move on with what you have to do. So we already know sort of what's going to happen here. We're going to have a transfer of electrons from our metal to our nonmetal because this is going to be ionic. So we could draw our Lewis dot symbols for lithium. Lithium is group number 1, which means it has 1 valence electron. And we could write our electron configuration, which I will, just to demonstrate what is going on here. And again, when we get to chapter 11, we'll officially talk about how to write those, but you may see it in chapter 12, obviously in the book, because they assume maybe you did 11 already. And once again, this second energy level is where we have our 1 valence electron. So that is the 1 valence electron that we're talking about here, or that we see in the picture. And for fluorine, that is group 7 on the periodic table, which means it looks something like this. It's got 7 dots to represent its 7 valence electrons. And if we write the electron configuration, 1s2, 2s2, 2p5. Once again, that's the second energy level. Second energy level, 2 and 5 is 7 valence electrons. So those are the 7 valence electrons that we see in the picture. The lower ones there are the core electrons, which are these. It'd be core electrons. All right, so because we know we have lithium, which pretty much is like, go ahead, take my electron, and fluorine is like, I will take your electron. That's basically what's going to happen here. The lithium is going to send its 1 electron over there to the fluorine in this case. It's at this point that the lithium has now lost an electron and will become positively charged. At this point as well, the fluorine will pick up that extra electron. And when it picks up that extra electron, it will now have a negative charge and becomes an ion. A lot of times people will put brackets between these two things, or maybe bracket both of them, to indicate that there is no sharing of electrons here, that the electrons have been transferred in this case. That is also why when you draw these Lewis symbols for ionic bonding, you do need to include the charges to also indicate that these are ions and that there are no sharing of electrons here. First off, any questions on that there? So let's see what happens in terms of the electron configuration of each of these things. The lithium gave away its 1 valence electron, which is that. That means that over here it has an electron configuration of 1s2. That's a total of how many electrons? 2. Who on the periodic table is number 2? It is helium. And that 1 electron that lithium sent over will actually end up right there in that 2p subshell, it's called, because it has room for it. And that fluorine with a -1 charge, or fluoride, will be 1s2, 2s2, 2p6. If we count up the top numbers, that is 2, 4, and 6 is 10 electrons. Who on the periodic table is 10? It is neon, yeah. So both lithium and fluoride here have reached the same electron configuration as helium and neon, which are both noble gases. Again, the whole purpose of bonding is that right there. They are what are sometimes referred to as being, I guess I shouldn't do both those guys together, but iso-electronic with each other as the same electron configuration. And really here, we are talking about lithium with a +1 charge and helium. And on this side, fluoride and neon. These two things have the exact same electron configuration. And as I was talking about earlier, they do not become those elements, but they have the same configuration as the electrons that helium and neon have. Any questions on that? So by transferring electrons here, the lithium was able to back up on the periodic table one spot to reach helium's configuration, and fluorine was able to gain an electron and go forward one spot on the periodic table to reach neon's configuration. Any questions on that? All right, let's take a look at another example here. Take a look at by the way, what that obviously is an ionic bond. And again, no sharing of electrons. The attractive forces between the positive ion and the negative ion is what holds that all together. So let's take a look at calcium oxide. So once again, calcium is group number 2 on the periodic table, which means it has 2 valence electrons. And again, I'll write the configuration so we can kind of see what's going on with that. 2s2, 2p6, 3s2, 3p6, 4s2. That 4 is the highest energy level there, and there are 2 electrons, and those are the valence electrons here for calcium in this particular case. Oxide is oxygen, which is group 6 on the periodic table. I'll go here. 2, 4, 5, and 6 has an electron configuration of 1s2, 2s2, 2p4. Once again, 2 and 2 are the highest energy level. 2 and 4 is 6 valence electrons. So those are the 6 valence electrons that we see here. So once again, in this particular case, what's going to happen is our calcium is going to send its electron over to our oxygen. Does calcium want to send just one electron or both? It does want to send both, because if it did just send one, if we just look at the periodic table, that would only move calcium one place back. Not a noble gas. So it actually does want to give away both of its electrons in this case. So the other electron will also come on over here to our oxygen. In this particular case, what happens is, I'll go underneath, calcium has now lost both electrons and become positively 2 charged as a result of losing 2 electrons. The oxygen will gain those 2 electrons, and because it gained 2 electrons from its neutral spot, will now become negatively 2 charged. And once again, at least a bracket on one of them to indicate that there's no sharing of electrons. So what happens with the electron configuration of each of these guys? Our calcium gets rid of its 2 valence electrons, which leaves it 2, 4, 10, 12, 18 electrons. Number 18 on the periodic table is argon. So it just became the same electron configuration as argon by losing those 2 electrons. That's good because the oxygen actually has space for those 2 electrons right there. And it will then fill in with 1s2, 2s2, 2p6. If we count the electrons, 2, 4, 10, that is neon's configuration. So once again here, by losing electrons, by gaining electrons, both elements here in this ionic bond have been able to achieve the same electron configuration as those noble gases. And that is typically what happens in the case of an ionic compound or ionic bond. The metal will lose enough electrons to back up on the periodic table to the noble gas that came right before it. The nonmetals will gain enough electrons to go forward on the periodic table to the noble gas that comes after it. Any questions on that there? All right, so what would happen here if we threw together 2 things we just looked at? Let's say we threw together here our friend calcium, which has our 2 valence electrons and our configuration there. And we put our fluorine, which is group 7, so it's got 7 valence electrons happening here. So now what happens is my calcium here is going to send my electron over to my fluorine. Once again, as we talked about, calcium does not want to get rid of just one electron. It wants to get rid of both. Can that fluorine take any more? Cannot, right? Because it will then have more than 8, which is not good for fluorine. So that's a problem because calcium does not want to stop at just getting to potassium. So in this particular case, we would need not one, but we would actually need 2 fluorines, which also has the same electron configuration, to take the extra electron there from our calcium. And now, as a result of this, what has happened is we will end up with a calcium that has a +2 charge. We will end up with 1 fluorine that gained 1 electron, and we'll end up with a -1 charge. And we will end up with another fluorine, I'll just draw it there, that also gained 1 electron and will be a -1 charge. Now, when we think about what happened to each of these elements as a result of gaining and losing electrons, good things happened in this situation. The calcium was able to get rid of both of those electrons like previously, 1 to each of the fluorines. That again leaves our calcium with 18 electrons, which means it is able to achieve argon's configuration. Each of the fluorines individually took in 1 electron individually, which means that moved each of them up to 10 electrons, which means both of these guys were able to achieve the same electron configuration as neon in this case. So all 3 of these elements were able to achieve that noble gas electron configuration by losing and gaining the appropriate amount of electrons. This ties into what we talked about at the end of chapter 4. If you remember when we talked about ions and putting ions together in a chemical formula, like if I had calcium with a +2 charge and I had fluoride with a -1 charge, when I put those together, the overall charge should equal what? 0, right? And this is really the reason why it should equal 0, because we need 1 more fluoride to accept the electron for the calcium, and that will give us our proper formula of CaF2. And this is really the reason why when we talked about putting a positive ion and a negative ion together in an ionic compound, that the formula should always have an overall charge of 0 in the simplest way possible. And that's because it allows each of those elements basically to achieve noble gas configuration and be very, very stable. So it's really the bonding part of it is why we put it together like that to equal 0. Any questions on that there? Questions on ionic bonding? Yeah. Okay. So ionic bonding, always metal, non-metal, always transfer of electrons, always results in ions being formed. When you draw these things, you do have to include the charges on those ions. And again, bracket up at least the negative guy to indicate that there's no sharing of electrons happening. Any questions? Okay. All right. Then let's talk about the other type of bonding, which is covalent bonding. And covalent bonding is different than ionic bonding. In covalent bonding, it is 2 nonmetals together. So that is definitely how you can distinguish between you have an ionic bond, which should be a metal and a nonmetal, and a covalent bond, which should be 2 nonmetals together. As I mentioned earlier, because of those periodic trends, when you have those 2 nonmetals together, they both really want to hang on to their electrons. So this is the situation where we're just going to compromise on sharing electrons rather than transferring electrons. So Gilbert Lewis, hence the name Lewis structures, Lewis dot symbols. He's like your bonding guy. Came up with really this idea of sharing of electrons. So we look at hydrogen, for example, and I got 1 hydrogen atom and another hydrogen atom. Clearly, those are both the exact same element, which they have identical periodic trends. They both are going to want to hang on to their electrons, so they're going to actually share. And the result of that is we will end up with a bond between the hydrogen atoms, where those electrons can be shared as are drawn as dots. You could also draw it as a line, as well to indicate that those electrons are being shared. And in this particular case, the 2 electrons in the middle here will count for the hydrogen on the left, and the 2 electrons there on the right, or the hydrogen on the right, will also count for that guy as well. So each of these hydrogen atoms will basically end up with 2 electrons, which is really good for hydrogen because that is all hydrogen needs. As I mentioned before, it just needs to get to helium in terms of its electron configuration. We can represent it with a line, and this is a covalent bond, and one line is represented by 2 dots, and that is a single bond. We also, as we will see in a later slide, can have 2 lines that represent 4 total electrons or 2 pairs, and that's a double bond. And we could also have 3 lines, which is representative of 6 total electrons or 3 electron pairs, which will be a triple bond. And as we'll talk about, in certain situations, sometimes you just need single bonds to make everybody happy. And in some cases, you may need double bonds to make people happy. And in certain cases, you may need triple bonds to make everybody sort of happy. Any questions on that? I personally will probably use lines to represent those electrons being shared as a bond, but you can use dots or lines in this particular case. So what is holding that together? Well, if you think about something like hydrogen, you got like the nucleus there in the middle if you want. Got these negatively charged electrons. So there's going to be some attraction to both nucleuses. So those electrons in the middle of the bond is attracted to the nucleus on the left, also attracted to the nucleus on the right, and that's what's going to kind of lock them in between the different elements. So let's take a look at an example of fluorine. In the case of fluorine, we basically have 7 valence electrons for each of them, as is group number 7. And once again, since they are both really the same element, they definitely have the same periodic trend. So those guys are going to be shared. And again, as you can see on the bottom there, you can represent it one of 2 ways, either with all dots, if you like. Or like we see down here, you could use the line to represent those electrons being shared. So once again, in this case, those electrons in the middle will count for both elements or both atoms. So this guy over here on the left will have 8 electrons, which makes it just like the noble gases. And those electrons being shared in the middle will also count for the guy on the right, which will give our guy on the right there 8 electrons as well. Again, in this case, the fluorine sharing electrons, allowing it to reach really that noble gas configuration and be really stable. Any questions on that there? So when we look at this type of structure here, there are different types of electrons, and all these electrons that are represented with dots here in this picture, these are all what are referred to as lone pairs, or most books nowadays will use non-bonding electrons. I would say probably most books use non-bonding electrons. I'll probably use lone pairs or a combination of both. So if I do say lone pairs, it's the same thing as non-bonding electrons. There are electrons, as the name implies, not involved in any type of bond. And that is, as we see here, no other elements on the other side of those dots. So there is no bonding happening there. There's also the electrons that are involved in a bond, which would be these guys right here. And they have a very special name known as bonding electrons. Very creative. So bonding electrons, again, as the name implies, are electrons that are being shared between 2 atoms within a bond. Non-bonding or lone pairs are electrons that are not really making any type of bond, but are still there. When you draw Lewis structures, and we'll talk about later on this chapter how to properly draw all these structures, you should always include all the non-bonding electrons and the bonding electrons in your actual picture. Bless you. So a Lewis structure, as we've been talking about, really is a representation of bonding, using either a combination of dots and lines to represent it. Again, only the valence electrons are shown. But again, they do have those core electrons, all these elements, but really do not participate in bonding. So if we take a look at another example like water again will share some electrons, actually in two locations here. And again, our hydrogen by sharing electrons gets 2 electrons. Our hydrogen on this side by sharing electrons gets 2. And our oxygen by sharing with both hydrogens, in this case, gets to 8. So again, it allows everybody to get to where they need to be in terms of sort of the two magical numbers of bonding, which is 8 and 2, mainly 8 in terms of getting to that noble gas configuration. So that officially is the octet rule. And the octet rule basically states that everybody will continue to make bonds until they have 8 valence electrons around it, except for hydrogen, which again should only have 2, as it only needs to get to helium to be good. And that is sometimes what is referred to as the duet rule. So I'll say this a couple times before we're done probably, but when you draw hydrogen, because it should only have 2, basically should look something like this. It also means that hydrogen should always be on the outside, because if you put hydrogen in the middle, it will have too many electrons, too many bonds. So it should really look like that, or if you choose to use dots, it should really look like that with something on the other side, but it should never have any more than that. I say that because when people start drawing Lewis structures, they draw something like this. They go, cool, I remember dots, so I'm going to put some dots around everything. Well, it looks more chemistry-ish if I throw a few more bonds on there. Before you know, poor hydrogen's got like 92,000 electrons, right? And you have a big X, yeah? So don't do that on your paper. So again, always on the outside, should always look like it does there on the right. Pretty much one line hydrogen, and that is it. It does not need any more than that. And it happens a lot. People just go crazy with the hydrogen. So as I mentioned before, in order to really get to this octet rule, and by the way, everything that we do in this class will pretty much obey the octet rule. When you go to 1A, you'll do a lot of not obeying the octet rule, but in here, everything will follow the octet rule. There are some exceptions we'll talk about, but everything that we draw in here will definitely obey that. So sometimes to get to the octet rule and meet the octet rule, really single bonds is sufficient. So everybody gets single bonds and everybody's okay. Sometimes you do actually need to maybe make some double bonds. So an example of that is carbon dioxide. It actually has a couple of double bonds on each side there. And in this case, the oxygen there, by sharing with the carbon, ends up with 8 electrons by making the double bond on both sides. And the carbon also, by sharing with the oxygen on each side, will end up with 8 electrons. So sometimes it's necessary to go to double bond, maybe not 2 double bonds sometimes, but you might need to get you to the octet rule. And sometimes it does require triple bond to meet the octet rule. So sometimes you do need to go to a triple bond like we see here with nitrogen, also ethylene. And again here, the nitrogen gets 8 electrons by triple bonding in the middle, and it allows each of those nitrogens to get to 8. I will say this probably a couple times as well. As I mentioned, we will be talking about how to properly draw these structures and sort of the rules you should follow when you draw them. But one thing that people also very commonly make mistakes on is they feel like they should like double bond, triple bond right out of the box because it again looks more chemistry like maybe. And that's usually will lead you in a lot of cases to not the greatest structure. So one thing to sort of keep in your mind is this, you usually want to start with single bonds when you're doing covalent bonding. And if somebody doesn't meet the octet rule, that's usually when we want to roll into making double bonds to try to fix it, or triple bonds if double bonds don't fix it. So Usually double bonding and triple bonding right out of the box is not the best idea in most cases. So just keep that in mind as we go through it. So let's talk about specifically covalent bonding and how we know, how the electrons are going to be shared. We could definitely use electronegativity, which is kind of the main idea of what we use to determine how electrons are going to be shared. We could also use electronegativity to help us with ionic bonds, but we really don't need to actually use it because as soon as you see metal and non-metal, it's ionic. So you don't even really need to worry about the electronegativity. This is really more for two non-metals together. You got two non-metals together. You want to know, how are the electrons going to be shared? Electronegativity, as I mentioned before, is the ability of an atom to bring electrons towards itself. Once again, it increases as we go this way on the periodic table, with fluorine being the most electronegative, and decreases as you go this way. And again, that's the ability to bring electrons towards itself, which is what it is. So let's talk a little bit about what happens in a covalent bonding when we have different types of sharing occurring. So if we have our bond here between our two hydrogens, like we looked at, these are both basically the same element, which is hydrogen, which means the electrons that are being shared between them are going to feel a pretty similar attractive force to both hydrogen atoms. So you could think of it like a rope, right? Tug of war. If you have two hydrogens on each side, they both are going to be pulling equally on that rope, right? So the rope's really not going to go anywhere too much. And that's what's going to happen with the electrons. So the result of this is because there's going to be sort of a equal attraction of those electrons between those two atoms, we will actually get equal sharing of electrons here. And when we get equal sharing of electrons, what that means as a whole over the bond, we have an even distribution of that negative charge kind of with the positive charge. And you could kind of think of this bond as being like neutral. There's no side that's more positive. There's no side that's more negative. Everything is going to be kind of shared pretty equally between those two atoms. And this type of bond is what is referred to as a nonpolar covalent bond. Most people will leave the covalent out of it and just call it a nonpolar bond, with the understanding that usually nonpolar involves two nonmetals and sharing electrons, so it's covalent. So nonpolar bond results from equal sharing of electrons between two atoms. They have very similar electronegativity. As we will talk about, there is sort of a difference. There is a little bit of a difference between what we considered equal sharing of electrons and truly equal sharing of electrons. This case here would be a truly equal sharing of electrons because they're both the same element, right? So they're going to pull perfectly identical to each other, and you will get something that's going to give you a perfect equal sharing of electrons, which sometimes people will call a pure covalent bond. Like perfect equal sharing of electrons. There are some where it's not perfect equal sharing of electrons, but close enough to be considered equal sharing, and it's still considered a nonpolar bond. So what happens though if I take away one of the hydrogens and I replace it with another element like, say, fluorine in this case? Between hydrogen and fluorine, is the electronegativity here the same? The answer is no, because fluorine is the most electronegative element you could have. It is further to the right and as far to the right as you could go. By the way, everybody further to the right than fluorine is the noble gases, which are chemically inert, don't look in the bond, have no electronegativity. And that's why we stop at fluorine here, because that is as far as right as you could go. So what this means is fluorine is going to, if you go back to sort of the tug of war example, going to be pulling that rope a lot harder than the other guy trying to hold on, right? And it's going to pull all the electrons closer to itself. So if this little yellow here is the electrons, we're going to have a big buildup of electrons towards the fluorine side versus the hydrogen side, because the fluorine is going to bring those electrons much closer to it versus the hydrogen. The result of that is it creates a little bit of problem here for our bond, because we now will have unequal sharing of electrons. And if the electrons are basically heading towards the fluorine, and I got everybody in terms of the electrons vacationing over there on the fluorine side, will the fluorine be more positive or more negative? If I have negatively charged electrons vacationing about the fluorine side, will it be positive or negative? Be more negative, right? Because you got a lot more electrons hanging out at the fluorine side. And what it will create in this case is what's referred to as a partially negative charge. That's a delta symbol, by the way, partially negative. And the hydrogen will actually gain a partial positive charge because the electrons are moving away from the hydrogen in this case. This type of separation could also be shown with an arrow, which is sometimes referred to as a dipole arrow, and it would head in this direction. It will always point to the more negative side of the bond, and the back part that kind of makes like a plus right here is the more positive side of the bond in this particular case. This unequal sharing of electrons, because really the difference in electronegativity of the fluorine wanting to bring electrons closer to itself, is what is known as a polar covalent bond, or just frankly a polar bond. Why does it create partially positive charge and a partially negative charge rather than a full positive charge and a full negative charge in this case? Why is it only partially positive and partially negative? What do you think? I got time. I don't have a watch, but I have time. It is because what is happening with these electrons? Are they being transferred or shared? They are still being shared, yeah? So they're still being shared unequally. So they haven't fully transferred. That's why they are only partially positive charges and partially negative charges. In the case of an ionic bond, those electrons are fully transferring from one to the other. So we gain full positive charges, which are cations, full negative charges, which are anions. If you go back to the rope example in this case, right, tug of war, the guy pulling the fluorine pulling tight, that poor hydrogen is hanging on and going through the mud, right, as he gets pulled around, hanging onto the rope, still hanging on. The electrons haven't fully transferred, and that's why they're partially positive and partially negative charges, rather than what we see in ionic compounds, where they just jump ship basically completely, and we get those complete charges. This type of bonding and these different types of bonding are important for things like how molecules interact with one another, solubility, boiling points, and things like that, depending on whether they have these type of bonds or not. So you can think of a nonpolar bond as kind of like a neutral. A polar bond is sort of a that has a charged side, a positive charge side, and a negative side. Any questions on that there? And so, as I mentioned, that is our polar covalent bond. That difference in electronegativity going to cause that difference in charge, and that partially positive and partially negative charge basically occurring. And again, can be represented with that arrow there. So we could think about sort of the three types of bonding that we talked about and sort of summarize it like this. On one end of the extreme, we have a ionic bond. which is always between a metal and a nonmetal, where we have that transfer of electrons from our metal to our nonmetal. Again, the result of that, as we talked about, our cation gets formed from the metal, our anion gets formed from the nonmetal. That electrostatic attraction holds that together. No sharing of electrons here. An example of that would be something like sodium chloride, right? Sodium is a positively charged ion. Chlorine is a negatively charged ion. The sodium gives away its electron to the chlorine, and the chlorine picks it up, and it gets a full transfer of electrons that happens. On the other end of the extreme, we have a nonpolar covalent bond, or just a nonpolar bond. And that is always between two nonmetals, where we have equal sharing of electrons. And again, a result of that is something like F2 or H2 that we saw earlier as well. Again, we're going to get this nice, perfect, equal sharing of electrons in a sense, going to not create any positive side or negative side to that bond, and that is what is known as a nonpolar bond. Sort of in the middle of those two types of bonds is our polar covalent bond, or just a polar bond. Also between two nonmetals, we have unequal sharing of electrons here, creating that positive side on one and negative side on the other. An example would be this guy right here, our HF, right? So one end of the extreme, we're just gonna get rid of our electrons, transferring them. Other end, we're just gonna share equally. In the middle is not so equal sharing, but it's not so unequal sharing that they transfer the electrons. There is some aspect of sharing. In the case of HF, it's a very small aspect of sharing. The fluorine almost rips them all apart and transfers them, but the hydrogen is still able to hang on a little bit. Any questions on the different types of bonding there? So as I mentioned before, that electronegativity really is the overwhelmingly sort of thing that we look at in terms of determining how electrons will be shared. And as I mentioned earlier, we really use it in most cases to help us determine how electrons will be shared in a covalent situation. That's usually what we would use it for. You again could technically use it, as we'll talk about, in an ionic situation. It's really not necessary because, again, you see that metal, non-metal, it's ionic. So really here, we will use electronegativity in a lot of cases to determine how those electrons will be shared between the two atoms, and will they be shared equally or unequally. And it is based on some of those periodic trends that we talked about: electron affinity, ionization energy. So things with very high electron affinity, which means they like electrons to gain electrons, and very high ionization energy, which means it's a heck of a time to try to remove electrons. So something like fluorine would have a high electronegativity, 1O, I suppose. High electronegativity because it's basically want to hang on to its electrons and take others. Sodium, on the other hand, has low electron affinity, which means it's not looking to gain electrons. It has low ionization energy, not really looking to hang on to its electrons. So it's going to have low electronegativity and be willing to sort of give those away. That is why when we look at the periodic table, right, the most reactive metals should be found where on the periodic table? Bottom left of the periodic table. That is all those periodic trends where everybody's just going to give away their electrons pretty easily. Most reactive nonmetal is actually upper right of the periodic table, like fluorine, because it has all the trends of I'm keeping my electrons and I'm taking yours, right? So that's going to make it very, very reactive. All right, I think this is actually a good stopping place to lay up.